that may contain the value of the population parameter. Okay, so let me write it over here. Confidence interval. Okay, there are two terms in over here. Okay, first one is the confidence and the other one is interval. So interval by interval means that we have a range of values. Okay, we don't have any specific value but a range of values, and the confidence is that we are sure that this thing most probably will be in the defined range. By this thing I mean the population parameter. Okay, so confidence interval is the estimate range estimate that may contain. Okay, we are not sure 100%, but we say that it may contain the population, the value of the population parameter or the population parameter. Okay, now what is the population parameter? Okay, so population parameter, this actually, it is the thing that we want to investigate the population for. For example, the factor, or we can say the phenomena, this is the the range estimate that may contain the value of the population parameter. I have defined population parameter over here. I will define it now, but this is the definition of the confidence interval. This is the definition of the confidence interval. Now I will define the population parameter over here. So population parameter is actually the factor or phenomena for which the population is studied. Okay, for example, we want to investigate the average age of GCC men. Okay, for GCC, you know that it is the Gulf countries. Okay, for example, I want to know about the average age that a man have in Kuwait, Saudi Arabia, all these, the GCC countries, the Qatar, the UAE, and all these. Okay, so now the average age is the population parameter over here. So this average age is basically the population parameter that we want to investigate. And the GCC men, actually, this one, this is the population. Okay, you understanding my point? Okay, so what we do actually with the confidence interval, we actually find things about the population of interest. For example, here we say that the average human age in the GCC countries. Okay, so the GCC countries, actually, this is the population, and the average age of men, this is the population parameter of investigation that we want to investigate. The population, the interested, the population parameter that we are interested in is the average age. Okay, so to understand the confidence interval, actually, we need to know about the sample and sampling and population and inferences. Okay, so let's start with the sample. Okay, we have two things in the confidence interval. Okay, the first thing is sample, and the other thing is the population. Okay, now these two are quite different things. Sample is very different from the population. The population is the overall complete data. For example, we take age of each and every man in GCC. So this is the population. Okay. Now, if we take samples, okay, for example, I take 100 samples from UAE, 100 samples from Qatar, 100 samples from Saudi Arabia, and for example, I take 100 samples from your country, Kuwait. So now I have a sample of 400 people. Okay. So, and the total population for these GCC countries, actually, for example, it is like, we say like it is 20 million. So now 20 million is the total population, and these 400 people is the sample representing, actually, as this sample is taken from these 20 million people. So this 400 people are representing the 20 million GCC men. Are you understanding my points? Okay. So this is how the sampling is done. Okay. We have a population, so we cannot take actually the data of the whole population. So what we do, we take small samples from the population and say that this sample represents the whole population. This is an assumption that it represents the whole population. However, there are, I may take like 400 people, okay, and my average age, for example, we are two people, okay, we are two people investigating the average age. Okay, now, for example, the first man is Anwar, who is a statistician and want to know the average age of the GCC man, and the second one is Yusuf, who is also a statistician and wants to know, the average age of the GCC man. Now I take the data of 400 people. This is my sample, okay? And it turns out that the average X bar is, for example, 65 years, okay? And Yusuf also take the data of the 400 people, he takes a different sample, and his average is like 71 years, okay? Now, both of these samples are representing the same population. We are taking the data, you take 100 sample from UAE, 100 sample from Qatar, 100 sample from Saudi Arabia, and 100 sample from Kuwait. I also take the same way, but my average is 65 years and your average is 71 years. Okay. So what this actually means is that these samples actually do not represent the population by 100% confidence. Okay. There may be the sampling error. This is called sampling error. Okay. We have two samples, and the sample one have an average of 65 and the sample two has average of 71. So this difference is actually the sampling error. Okay. So this sample that we take, it does not by 100% represents the whole population. Okay. So the confidence interval actually cover up this sampling error, this margin of error. The confidence interval is used to cover up for these sampling errors. that you have to understand. This is the kind of the essence of confidence interval. Okay, because we have sampling errors. So to cover these sampling errors, what we do, we take the confidence interval of that population based on those samples. Okay, now I will come up. Yes, yes, I'm coming to that. I am coming to that, but before I want you to understand actually the confidence and not just, just write the formulas and, if the teacher give you, the problem like, yes, I want to know the stuff actually, the actual thing. We can come to the formulas and all that, and I will prove you, that all those things, and I will solve that those things. But if you know these things, I guess, in my view, if you know these things actually, you can, better if I say something in the lecture, you can just, quickly pick it up. Okay, he's saying about this thing. So that is why I'm going through this stuff. Okay. Now we have like inferences is like the kind of conclusion about the population. And these inferences are also based on sampling data. Okay. We make inferences or conclusion about population, but it is based on the sampling data. Okay. So we know that since the sample actually a proportion of the whole population, so it cannot be a pure or perfect representation of the population, just like we said in taking these two samples. So it must have errors, and these errors are called sampling. Okay. Now I will go further towards the confidence interval and how to kind of calculate it. Okay. So we have in sampling, we have sample mean. Okay. And we have sample standard deviation. The sampling standard deviation is represented by S, and the mean is represented by X bar. Okay. Now, in the confidence interval, actually, for example, this is the data, and this is the mean of the data, actually. Okay. Now, by the confidence interval, actually, we mean that, for example, we take an age of like 65 years. Okay. We say in the confidence interval, we actually say that we are like 95% or 90%, or this is the kind of surety that we have, that we are 95% confident, for example, that the 65 years actually mean it lies in the population. For example, we have a data over here, a single point over here, a point over here, point over here and a point over here. So by confidence interval, this is the confidence interval, you know, we are this much sure that this point actually lies within the range. Okay, so we have like a width for the confidence interval. Okay, so confidence interval can be of different widths. Okay, and it depends upon the sample size and the variation in the we have a width of confidence interval. Now, if we say that the mean, for example, the mean or average age lies between 55 and 65. Okay, so the width over here is 10 years. Between 55 and 65, we have 10 years. So the width is 10 years. When we say that the average age lies between 45 and 70, okay, we know that the confidence interval width is 75 minus 45, sorry, 70 minus 45, it will give us 25, okay, 25 years. Now, here the width is only 10 years, but here the width is 25 years. So this data actually has a longer width than the first one, and this width actually depends on two things. Okay, this width actually shows the accuracy of the confidence interval. Okay, now it depends on two things. The first one is the sample size, and the other thing is the variations in population or sampling. Okay, now if we take a small sample size, okay, if we take small sample size, it means that we have less data. Okay, and when we have less data, it means that we cannot be like that percentage of we have that percentage of surety. So the small sample size will give you a higher width of confidence interval, or you can say that the margin of error when sample is small is high. Okay, the margin of error is high when we have small sample size, and vice versa, which means that if the sample size is high, like for example, if I say that the sample size I take was like 400, and this is S1, sample size 1, and the other one was 1000, this is second sample. So which one will have like the confidence interval, better confidence interval? The S2, which has 1000 samples being investigated, because it has the higher data. Okay, it has low data, so we cannot be like that percentage of, we cannot bring that confidence in saying that the mean will be this. But in this one, we are pretty much confident that the mean will be between this and this. Okay, and the other thing is the variation in population. If the population variation is high, it means that the confidence interval width will also be high. Will be high if variation is high. But if the samples, all the samples are of the same size, for example, we want to know the average size of an apple in an orchard, okay? And like 500 apples from the population. We have a population of millions, but we take the 500 apples or 1000 apples and investigate that sample size. So if the apples are like they have a large variation between, for example, the first one apple that we investigate is 25 grams, but the second one is like 125 grams. Okay, we have like very high variation. Then the confidence interval width, CI width, it will be high, and we will be not that sure that the mean will lie in between this range. But if we pick like 10 apples and all the apples are of like 60 grams, 62 grams, 58 grams, the density is the if we plot it in the box plot, the data is like this. They are very that is the data is dense. It is like closely interacting to each other. Then we say that the confidence interval will be of lower weight, and we will be pretty much sure that the average size or the average weight of the apple in population will also be pretty much close to the sample data. But if the sample has variation, then we are not that we can say that we are not that much sure. Okay, so, so it means that the large confidence intervals mean that the variation will be high and we are less sure. And the small confidence interval means that the variation is low, the sample size may be high, and the confidence interval is also good, and we are pretty sure. Now, I will, make the calculation part. Okay, we will come to the calculation part, and we will say what is actually the confidence interval in the equation form. Okay, so for example, we want to investigate the population parameter. We can say that calculating confidence interval. Okay, so we have a population, and the population parameter in focus or in investigation is the mean x bar. Okay, and we say that the confidence interval, it is actually x bar plus minus margin of error. Okay, now the population, the sample mean is equal to x bar, the sample size is equal to n. Okay, and the standard deviation of the sample is actually the denoted by s, and it is equal to x divided by under root n. Sorry, s by under root. Yes, x by under root n. Yes, and we say that ci is equal to x bar plus minus margin of error. Okay, now we have x bar. This is based on the sample data. This is not the population data, but on the sample data. And we have to find the margin of error, and we add it or subtract it from the sample mean, and we get the confidence interval for that population. Okay. Now, the margin of error, this is equal to z alpha by 2 into the standard error. Okay, and this standard error is actually equal to the standard deviation by under the root n. Now, here is the tricky part actually. Okay. What we said previously, we said that if the sample size is high, then we have more information and the standard error will be less and we will be more confident in finding the confidence interval. So here is the part actually. Now if this n is high, okay, if this n is high, for example n is tending to be infinity, for example we have a very large population, then the standard error it will be close to 0, very small. Yes. So when the error is very small, then we say that confidence interval is equal to x bar plus minus z alpha by 2 into standard error. Now we know that standard error is equal to 0. Okay. So the confidence interval, it will be equal to the x bar. And this will, tend to be a point estimate then. It will not be a range then. It will be a point estimate. You understand this point? Yes. So if the sample size is very, we can pinpoint that this will be the mean of the whole population. Okay. And if the sample size is large, but not that large, that we can pinpoint the population mean, we can give like very small confidence interval range actually. Like for example, we can say like between 65 and 67. So see, this is very, close confidence interval. It means that we have high surety. And why we have high surety? Because the sample size is pretty, good. And same stands for the standard deviation. Okay. Now we know that the variation, okay, variation in data, the standard deviation is equal to under the root in the variation of the data. So if the variation is low, then the standard deviation is also, it also will tend to be 0. And when this is 0, it means the standard error will be 0. And again, we can pinpoint it, the point estimate. We can give a point estimate, a single point estimate for the confidence interval. So this was the thing that I did was actually to verify my points that I said earlier, and also to find the confidence interval in a mathematical form. Okay. Now, carrying it on, we say the confidence interval is equal to x bar, which is based plus minus the margin of error. Now the margin of error is equal to z alpha by 2 into the uh, standard error. And the standard error is actually equal to s divided by under root n. So we can say that x bar plus z alpha by 2 into s divided by under root n less than or equal to confidence interval bar minus z alpha by 2 s divided by under the root n. So this is giving us the confidence interval, and its probability will be equal to 1 minus alpha, where alpha is equal to significance level. Okay, so that is how we find the confidence interval. Here we say that it is mean. The population parameter that is in investigation over here is the mean of it. You understand my point? Okay. So let's do the first problem on the confidence interval. Okay. First, I will do the problems that are given by the professor, and then we can come to. Okay. So the the notes says that question 1, it says that we have a random sample of size n is equal to 100. Okay. Sample size n is 100, that is given to us, and it is from a Poisson distribution with parameter lambda. You know that when we have Poisson distribution, the x bar is actually equal to lambda. Okay, the result sample gave x bar is equal to 2.88. So this is equal to 2.88. For the large sample, 95% confidence interval of lambda, we want to know that if n is greater than 30, it is considered as large sample. Okay. If the size of sample is greater than 30, it is considered as large sample. Okay. We have n is equal to 100, so it is a large sample. And x bar is equal to lambda is equal to 2.88. Okay. And they want us to calculate 95% confidence interval. So probability over here, it is equal to 1 minus alpha. So here alpha is equal to 0.05, because 95% is equal to 1 minus 0.05. Okay, it will give us 95%. So we can calculate alpha from this confidence interval that we want to find the for. Okay, now for the confidence interval, what we actually have is we have x bar plus z alpha by 2 into standard error. Okay, now standard error is e is equal to, as we don't have any standard deviation over here. Okay, we don't have any standard deviation, so it will be equal to this thing, x bar divided by n whole under the root. Okay, when we put the values, we say that x bar is 2.88 divided by n is 100 under the root. It will give us, let me calculate it, under the 0.288, and taking the square root of it, we will get 0.169, or we can say that 0.17. Okay, so we already know that alpha is equal to 0.05 and the standard error is equal to 0.17. Now we can calculate the confidence interval. So confidence interval over here will be lambda plus minus r. We can replace lambda by x bar. Okay, anyone that you want to put. Okay, plus minus z alpha by 2 into SE. Okay, so we can say that 2.88 plus minus Z 0.05 divided by 2 into 0.17. Okay, we can also say that we have two values over here, 2.88 plus Z 0.025, because Z 0.05 divided by 2, it will give us Z 0.025, okay, into 0.17, and 2.88 minus Z 0.025 multiplied by 0.17. These two we need to get, okay, and the mean of this data will be in between these two with probability of 95%. We will be 95% sure that the mean lies between these two ranges. Okay, so Z for 0.025, we will use the Z table. Using Z table, from Z table, actually Z of 0.025 is equal to 1.96. Should I show it to you, or you know that how to read the table? Yes, you just need to know the level of significance and the confidence that it will be like in this form. Okay, N, and here it will be the actually the alpha, this way, 0.025, 0.05, and 0.075, and so on. Okay, and it will be the sample size 1, 2, 3 up to. So you need to know the 100 and this. So it will this point will give you the exact value, and it will be 1.96. Okay, that is how we read the table. Okay, if you have internet, you can just search Z value for 0.025, and it will give you 1.96. Okay, so 2.88 plus 1.96 into 0.17, comma 2.88 minus 1.96. Okay, so there are certain conditions then that when they are met, we actually use the T distribution or Z distribution. Okay, so the first case is when the Poisson distribution is given, then we take lambda is equal to x bar. Okay, and we will use the Z distribution. Okay, we can also use the T distribution over here. Okay, but it depends upon the sample size. Okay, and we can find the standard error, and it is equal to under the root lambda by n, where n is the sample size. Okay, and lambda is equal to x bar, or mean of the sample. Okay, and the confidence interval, it is equal to lambda plus minus z alpha by 2 into standard error, while standard error is equal to the root lambda divided by n. So putting the values over here, we get confidence interval is equal to lambda plus minus z of alpha by 2 into under the root lambda by n. Okay, so this is when we have Poisson distribution. Okay, there is also another case. Okay, to differentiate between the T distribution and Z distribution, like when to use Z slash t distribution or tables. Okay, so we have actually certain conditions. When they are met, we use z distribution, and when they are not met, then we use the t distribution. I will shortly explain the conditions. For z distribution, following are the for z distribution following are the major conditions. Okay, the first thing is that the population must follow normal distribution. We will use the z value if the population is following the normal distribution. If it is given that the population follows normal distribution, then we go for the z distribution. But along with this condition, we have two other conditions also. The next condition is that the sample size must be greater than or equal to 30, which means that there is sufficiently large sample. Okay, sample greater than 30 is considered as large sample. Okay, so the sample size must be greater than or equal to 30. Then the z distribution or z value will be used in the measurement or estimation of the confidence interval. The third one is that the population standard deviation, actually it is known. The third one is that we have the population, not the samples but the population standard deviation, sigma. When the population standard deviation is known to us, then we use the z distribution. Now for t value, or for the t table, actually, okay, here the confidence interval will be equal to x bar plus minus z alpha by 2 into standard error. Okay, or x bar plus minus z alpha by 2 into standard deviation divided by under the root n. Okay, so this is the confidence interval for when these conditions are met. Okay, we use z over here. Okay, and why we use z? Because it meet these three conditions. Okay, now I will go to the t table when we use the t distribution. Okay, the first condition is that when the sample size is less than 30, implies that n is less than 30, or when the sample is small. Okay, then we can use the t distribution, and the population standard deviation, also called sigma, is unknown. Then we use the t value. Okay, and population must follow standard normal distribution, must follow normal distribution. Okay, so this third condition, this one, the population must follow normal distribution, it is common for both z and t, but the contrast is in z, we use z value when the sample size is greater than 30, and we use t value when sample size is less than 30. Other than that, the standard deviation of the population, which is sigma, in z it is known, and for t, when it is unknown, we use the t table. And the value of the confidence interval here, it will be x bar plus minus t alpha by 2, okay, into standard error, okay. And we know that standard error is the standard deviation of sample, standard deviation divided by under the root n, okay. Now we will use these three conditions, and we will solve some problems based on these conditions. Okay, so the example is that we have a sample of 400 people, okay, and the mean length of men or average height, it is equal to 1.75 meters, okay. Now the population follows normal distribution. It is given to us, okay, that it follows the normal distribution, and the population variance is also given, and population variance is equal to 0.16, okay. So variance can be denoted as the population variance is equal to sigma square, and it is equal to 0.16, okay. And we know that standard deviation is under root of the variance, okay. This is a hint, a formula that is used very frequently, okay. If we are given the variance but not the standard deviation, then we can use them interchangeably to find, for example, if we have like standard deviation but we don't have any variance given, okay, then we can find variance from it, and if the variance is given for the population, then we can find the standard deviation from it, okay. So this is the formula being used, okay. Now it says that the question that demands is that find 95% confidence interval for average height, okay. So the population parameter, actually we will start the solution process. So the population parameter that is in the consideration, it is the average height or mean. Actually we want to find the confidence interval for the average height or mean height, okay. So that is the population parameter, okay. Now sample is equal to 400, okay. It is greater than 30, so the first condition for the Z distribution is okay. Now it also says the population follows normal distribution, okay. So we can either use T or Z value over here, because it is common for both, but we know that the population, the sample size is 400, which is greater than 30, which means that it is large sample. So when it is large sample, we use Z distribution, and other than that we have population variance, okay, which is equal to 0.16. so this question actually all it follows the conditions for the Z value. So the confidence interval here, it will be equal to x bar, which is the average mean height for the sample that is collected, 400 people, plus minus Z alpha by 2 into standard error, okay. Now we know that standard error is equal to standard deviation divided by under the root n, okay. So we can actually put the value over here, But first we will find the standard deviation. So standard deviation is equal to under the root variance. Okay, now under the root 0.16, it will give us a value of let me calculate it. Under the root 0.16, it gives a value of 0.14. Sorry, 0.4, not 0.14 but 0.4. It is the standard deviation value. Now we have standard deviation over here, okay, and we have n over here, so we can find the standard error. So SE is equal to 0.4 divided by under the root 400. Okay, under the root 400 will give you a value of like 20. So 0.4 divided by 20, and it will give you a value of 0.02. So the standard error is 0.02. Now to find the confidence interval, we have x bar plus minus z alpha by 2, okay, into standard error. Now we have standard error found. We have x bar, which is 1.75 meter, that is already given. Okay, so we need to find alpha by 2 value for z. Now alpha is equal to, as it is 95% confidence interval, which implies that alpha is equal to 1 minus 0.95. So alpha is equal to 0.05. Okay, this is the significance level. Okay, and alpha by 2, it will be equal to 0.05 divided by 2, which will give us 0.025. So from z table, z of alpha by 2 is equal to z 0.025, and it gives us a value of 1.96. Putting the value over here, we get confidence interval is equal to 1.75 plus minus 1.96 into 0.02. So it will give us a value of, it will give us a range which is 1.75 plus 1.96 into 0.02 and 1.75 minus 1.96 into 0.02. Okay, now doing this, we get the confidence interval of 1.789 and 1.7108, which means that the mean height, it will be somewhere between these range. Okay, and that is the confidence interval for the population. This is the 95% confidence interval being found. Okay, in the previous video, actually in the lecture video, I wrote it t of alpha by 2, but in the t table we have two things. We have the degree of freedom also, so it is t alpha by 2 comma n minus 1. Okay, this is the degree of freedom for the number of samples. Okay, because from the t table, if you want to find the value of t from t table, we use significance level as the degree of freedom. Okay, so that is one correction that's needed to be made. Now we will move forward to the other problems. Okay, so we will now do example 2. Okay, so in this example, it says that if a random sample of size n is equal to 20, okay, if a random sample of size n is equal to 20, it means that the sample size is 20 and it is less than 30, so it is a small sample, okay, from a normal population, it means that this population is following the normal distribution, okay, with variance sigma square is equal to 225 and has mean of x bar is equal to 64.3. Construct a 95% confidence interval, okay, so we will now solve it, and to start the solution with, we first see if it falls under the category of the Z table or the T table, okay. So the first thing is that we have a sample size of n is equal to 20, which is less than 30, so it is a small sample, okay, and it follows normal distribution and with variance of sigma square is equal to 225, so it means that this is the variance of the population, okay, so this is the variance of the population, okay. If it were the variance of the sample, it would be s square, not the sigma square, okay, so that is the difference, okay, and it has a mean of x bar is equal to 64.3, which is the mean for the sample, n is equal to 20, okay, and it says the construct a 95% confidence interval, so we know that the confidence interval is equal to x bar plus minus, we will use z over here, okay, and standard error, okay, or we can directly define it as x bar plus minus z of alpha by 2 into now we use this equation, okay, because it has standard error and it has the direct values over here, so this one is better to use, okay. Now x bar is equal to 64.3, it is given to us, okay. Standard deviation is unknown, but variance sigma square is equal to 225, so standard deviation is under the root of sigma square, so it is under the root of 225 and it will give us a value of 15, okay, so the standard deviation for the population is 15. Now Ci, the confidence interval, is equal to 64.3 plus minus Z of, it is 95%, so for 95% confidence interval the alpha value is 0.05 and alpha by 2 will be equal to 0.05 divided by 2, which will become 0.025 multiplied by the standard error, which is equal to 15, because we found standard deviation and under the root of 20, okay. So confidence interval is equal to 64.3 plus minus z of 0.025 into 15 divided by under the root 20 will give us 4.472. 4.472, and z of 0.025, it yields a value of 1.96. So putting these values, we get 64.3 plus minus 1.96 into 15 by 4.472. It will give us 3.3542. Okay, so the confidence interval is equal to 64.3 plus minus, and this when multiplied it will give us a total value of 6.57. So we add this and also subtract this. Okay, so the confidence interval is equal to 64.3 minus 6.57 and 64.3 plus 6.57. So we will get confidence interval of this will give us 57.7, while this one will yield a value of 70.9 approximately. So it means that the mean of these 20 samples, okay, this the mean of the population from which these 20 samples is taken, actually it will be somewhat between 57.7 and 70.9, and we are 95% confident about it. Okay, so we are 95% confident that the mean of the population is somewhat between 57.7 and 70.9. So this is the range of the mean for the population, actually, not the sample, the population. We have another question which says that, question 3, which says that a plant manufacturer wants to determine the average dyeing time of a new interior wall paint. Okay, he wants to find or determine the average dyeing time. Okay, so the population parameter is equal to the average dyeing time. This is to be found. The confidence interval for this average dyeing time is to be found. Okay, if for 12 test areas of equal size he obtained a mean of 66.3 minutes. So the mean dyeing time for n is equal to 12 samples. It means that the sample size is small. Okay, so there is a chance that we can use t table over here. Okay, so let's proceed in the question and see that if any other quality or characteristics is there, so that we can use the t distribution. Okay, now the first thing is n is equal to 10, which is qualified for the t distribution, but let's progress with the okay. Now it says that the mean dyeing time, okay, mean dyeing time for the sample x bar is equal to 66.3 minutes. Okay, the mean dyeing time is 66.3 minutes. Now other than that, the standard deviation for the sample, okay, it says that if for 12 test areas of equal size he obtained a mean dyeing time of 66.3 minutes and standard deviation of 8.4 minutes. So it means that the standard deviation that he found is S, it is for sample, and it is 8.4 minutes. Okay, if it were for population, it would say that the mean standard deviation or the standard deviation for the population is this, that. Okay, but it is for sample, so they does not mention any of the population. It says they construct 95% confidence interval. So we'll go towards the solution. Now we say that the first characteristic is that the sample size is small, it is 12, it is less than 30. Okay, and we don't have the population standard deviation is unknown. Okay, so when the population standard deviation is unknown, it means that it qualifies for the t distribution. We use t test values or t values. Okay, now for this, the confidence interval will be equal to x bar plus minus t alpha by 2 comma n minus 1 multiply by the standard error, which is equal to s divided by under the root n. Okay, we put s over here because this is the sample standard deviation. Sample standard deviation is known, but the population standard deviation is unknown. Okay, so the confidence interval is equal to x bar plus minus t of, it is 95%, so alpha is equal to 0.05. So alpha by 2 is equal to 0.025. F and n is equal to 12, so n minus 1 is equal to 11 multiply by s. Okay, divided by under the root n. Okay, now x bar is given to us, which is 66.3. okay, plus minus, we will get this value from the t table. I will show it to you, and v t of 0.025 and 11 multiply by s is given, which is 8.4, and under the root n is under root 12. Okay, so let's find this value from the t table actually. Okay, so we want to find t for 0.025 and 11. So the degree of freedom is 11 because we have 12 samples, so n minus 1 will get us 11. So the degree of freedom is 11, and the significance level is 0.025, so it will give us a value of 2.201. This is the value. This is 0.025 and 11, it is 2.201. This is the value that is calculated over here. This is how we use the t distribution critical values to find the confidence interval. Okay, now here we put 2.201 and we get 66.3 plus minus 2.201 multiplied by 8.4 divided by under root 12. So under the root 12 will get us a value of 3.46. Okay, so 66.3 plus minus 2.201 multiplied by 8.4 divided by 3.464. Okay, so this factor will get us a value of, let's calculate it, 2.4249, which becomes 2.425. So 66.3 plus minus 2.201 multiplied by 2.425
2.425. So we get 66.3 minus 2.201 into 2.425 and 66.3 plus 2.201 into 2.425. So calculating this, the confidence interval is equal to 66.3 minus 5.337 and 66.3 plus 5.337. So the lower bound will be equal to 61 or 61, I guess, because 0.3 and 0.3 this will subtracted equal, and 66 minus 5 it will give us 61. So it will give us about 61 approximately, and here we will get 0.6 in the second part and 71, so 71.6 something. This is the confidence interval for the, so we are 95% confident that the value of the mean, actually the average dying time for the whole population or the whole process, is somewhere between 61 and 71.6. okay, and the probability is 95%. We are 95% confident. It means that there is still 5% chance that the mean dying value, it does not fall in this range. Okay, it may occur that it does not fall, like I take a sample and it may not fall into this region, but most of the time it will fall, and by most of the time I mean that about 95% of the time. Okay, so we have another example which is for a single mean or a single sample actually. So it is also a single sample problem, and it says that an automotive engineer actually wants to estimate the cost of repairing a car that experiences a 25 miles per hour head-on collision. Okay, so the population parameter is equal to the mean cost of repairing a car which has collided at a speed of 25 miles per hour. Okay, so he crashes 24 cars. Okay, so he took the data of 24 cars. It means that the sample size is 24 cars. So it says, the question says that he crashes 24 cars and the average repair is $11,000. So average repair, which is X bar, is 11,000 US dollars. Okay, and the standard deviation of the 24 cars sample, standard deviation of the 24 car sample, so it means that it is a sample standard deviation S. Okay, it is $2,500. Okay, so it says that provide a 98% confidence interval, provide or construct 98% confidence interval for this mean cost of repair. So we will solve this. So the sample size is 24, which is less than 30. Okay, a small sample, so we will use the t distribution. Now, and why t distribution? because first thing is that the sample size is less than 30. The second thing is that we have the sample standard deviation and not the population standard deviation. Okay, so these two conditions makes it a qualified problem for the t distribution. Okay, so for the t distribution, the confidence interval is equal to x bar plus minus t of alpha by 2 n minus 1 multiplied by the standard error, and standard error is equal to s divided by under the root n. So first we want to know how many things that we have available over here. So x bar is available, which is 11,000. Okay, n is available, which is 24 cards. S is available, which is $2,500. Okay, we only need to know about this thing. So t alpha by 2 n minus 1 is equal to t alpha is, we want to know the 98% of confidence interval. So alpha here is equal to 0.02. So t of alpha by 2 is 0.02 divided by 2, and n minus 1 means that it is 24 minus 1. So it gives us 0.001, I guess. Yes, and 23. Okay, and we will use the t table to find its value. Okay, so we have a t table over here on the PC, and we will find the value of it. Okay, so the degree of freedom is 23, and the significance level is 0.01. Okay, so we get over here the degree of freedom is 23 and the level of significance is 0.01. 21.3 into 0.01, it gives us a value of 2.5. Okay, this is the value that we need over here. So from the t table, the value is 2.5. Now Ci is equal to x bar is 11,000 plus minus this value is 2.5 into s is equal to 2,500 divided by under the root 24. So let's get the value of this factor actually. So dividing 2,500 by square root of 24, so the square root of 24 actually gives us 4.9 value. Okay, so 2,500 divided by 4.9, it gives us 510.2. so it gives us 510.20. Okay, now multiplying these two factors, so multiplying that with 2.5, it gives us $1,275.5. Okay, so it is $11,000 plus minus $1,275.5. Okay, so the confidence interval, which is actually 98% confidence interval, is equal to 11,000 minus 1275.5 comma 11,000 plus 1275.5. So the range that we get over here is this addition. It will give us 12,275.5. Okay, and the subtraction, it will give us 9724.5. So this is the range actually in which the mean cost of repair will fall. One more example on the single mean problems, and then we can move to the two means or two samples confidence intervals. Okay, so here it is a problem in which it says that a sample of n is equal to 56 observations of O2 consumption by adult western lizards gave the following statistics. Okay, it means that the sample size of the lizards is 56. Okay, 56 lizards were actually studied for the O2 consumption. Okay, and the population parameter is the mean O2 consumption, oxygen consumption. Okay, and it says that it gave us the following statistics. In the statistics, it is written that the mean was 249 mm cube per gram per hour. Okay, and the sample standard deviation, not the population but the sample standard deviation of 24 mm cube per gram per hour. Okay, and it says that find 90% confidence interval for mean O2 consumption. Okay, so to see whether it qualifies for the Z or the T distribution, we first think that what is the sample size. Sample size is 56, which is higher than 30, so it is large sample. But the catch is that we are given the sample mean, which is also given for the Z distribution, but the difference is that it is given the sample standard deviation and we don't know about the population standard deviation. So when we don't know about the population standard deviation and we are given the sample standard deviation, then we use the T distribution. Okay, it means that the confidence interval here will be equal to x bar plus minus T alpha by 2 n minus 1 multiplied by the standard error. Okay, s by n will give us the standard error. Okay, so x bar is given, which is 249 plus minus, we want to have like 90% confidence interval. It means that alpha is equal to 0.1 and alpha by 2 is equal to 0.1 divided by 2, which gives us 0.05. Okay, 0.05, and n is equal to 56, so the degree of freedom for samples will be 55 multiplied by s is given as 24 and n is given as 56, so under the root 56. So simplifying it, we will get the desired value. Now confidence interval is equal to 249 plus minus. We want to know the value of t 0.05 and 55. Okay, it will be taken from the t table. Okay, we will open the t table on my PC and let's see what value we get for this t. The significance level of 0.05 and the degree of freedom of 55. Okay, so here the degree of freedom is, we don't have a 55 over here, but let's, because after 50 it is somewhat like equal. Okay, so it will be equal for 50 and 55. Okay, because for 50 and 60 it is equal, almost equal. So we take this and the level of significance is 0.05. So it will get us a value of 1.676. Okay, 1.676 is the desired value. Putting the value here, 1.676 multiplied by s is equal to, let me see what is the value of s again from the question. S is equal to 24. So 24 divided by under the root 56. So let's first find under the root 56 is equal to 7.48, or we can round it off to 7.5 actually. Okay, so the confidence interval is equal to 249 plus minus 1.676 into 7.48 divided by 24 divided by 7.48. So let's calculate the value of this factor and multiply it with this to find the margin of error. Okay, is equal to 249 plus minus, let's calculate this margin of error and add and subtract it to the mean value. So first of all, 24 divided by 7.48 will get us a value of 3.20. Okay, so 1.676 into 3.21 when rounded off. Okay, now if we multiply it to 1.676, it gets us a value of 5.4 actually. So 249 plus minus 5.4. So the confidence interval is equal to 249 minus 5.4 and 249 plus 5.4. So it will give us the value of, on the upper level or the upper bound, it will get us a value of 254.4, and at the lower it will give us a value of 243.6 approximately. So this is the 90% confidence interval.